This video series is on section 5.2 in our textbook, which makes the connection between the algebra and geometry that we were doing in 5.1 with areas of rectangles to calculus. So here's where we make the jump from algebra and geometry to calculus. So one thing I need to show you first is what's referred to as sigma notation. Sigma is basically the Greek letter, or the Greek letter equivalent to our English letter S. And it's equivalent to the English letter S because the word it stands for is sum. So that's why we're using the Greek letter S. So the letter in the Greek alphabet looks like this. This is the capital sigma, anyways. And again, that's capital letter S in Greek, and it stands for sum. So the notation that is referred to as sigma notation, this is sort of the general form of it, is you have this big capital Greek letter sigma. You have this, we call a dummy variable, meaning it doesn't matter what we call it. A lot of times we call it K. K is going to begin at sum number 1 and end at sum number n. And then to the right, you have, this expression that is related to the K. And what it means is the first term in this sum would be a sub 1, because we begin with 1. The second term would be a sub 2. The third would be a sub 3, all the way to the nth term. And so basically you have all of these n terms. Again, n is the number of terms. And you add them, or you sum them up. That's what the big capital letter sigma stands for. So just a couple of sort of generic examples would be, let's say you had the sum from 1 to 4 of k squared. So k is just some dummy variable, and I'm going to do this to the variable for 1 to 4. So this would be equivalent to 1 squared plus 2 squared plus 3 squared plus 4 squared. I would stop there because I hit 4. I would add all of that up. 1 plus 4 plus 9 plus 16. And that would be 5 plus 9 is 14 plus 16 is 30. So notice how this ends up equaling one number. And that's kind of how the sigma notation works. For another example, let's say you had the sum, again that's capital letter S, from 1 to 5 of 2k minus 3. Okay, so then the first term would be 2 minus 3 plus 4 minus 3 plus 2 times 3, 6 minus 3 plus 8 minus 3 and then plus 10 minus 3. Figure out what each of those terms would be, add them up, and that would be what the sum is equal to. So that's how the notation works. Now we're going to carry that over to what is referred to as a Riemann sum. Whoops, there it is. That, of course, was named after a mathematician, as most of our names and theorems are. And it refers to what we did in class today and what we learned in 5.1. So before I give you the notation for it, let's kind of look at the generic example of finding an area between, or under, I should say, under the curve of some function and above the x-axis. So the kinds of things we were dealing with in 5-1. So here we have x and y. And let's say we have some curve, some fancy curve, f of x. We mark off some endpoints, a to b, and we basically are in search of this area. Let me make it a little bit less rectangular looking, just to kind of drive the point home. Okay, and so the way that we attempted this problem was by splitting this into small rectangles. So we wanted to turn a complicated problem into a lot of little not so complicated problems. And so we would split it up into some subintervals. So I'll go ahead and just make some subintervals. And so maybe I'll call this x1, x2, x3, x4, x5, x6. And this will be x sub n. And then a would be x sub 0, the initial one. Okay, so I now have 1, 2, 3, 4, 5, 6, 7, but instead of 7, we'll just call it n subintervals. Just to kind of keep things general. Notice also that the change in each nth subinterval, since I split it evenly, would be the entire distance between a and b. So if I subtract b minus a, I'd figure out the difference between them. And if I take that and divide it by how many intervals I have, that would give me the length of each subinterval. We'll go ahead and call that delta x sub n. We're going to call that delta x sub k, since n is referring to how many intervals. K is just a dummy variable, so we can keep track of what interval I'm talking about. Okay, so we know the distance between all the x's is equal because we're going to split it up evenly. And then now I go ahead and find all of the heights. Well, I think we can agree that when we were doing the 3 different kinds, the left endpoint, the midpoint, and the right endpoint, the one that was most accurate were the midpoints. They had the least amount of error when we were doing, all the different kinds. So maybe to draw our rectangles, we'll use the midpoints as our heights. Okay, so I have all my heights drawn in using my midpoints to determine the heights. So we could say then that my heights, so these are the base of each rectangle. I could say then that the height would be f of, and then I'm going to go ahead and give each of those little midpoints a name. And I'm going to call this one C1, C2, sorry, so tiny, C3, C4, C5, C6, and then I'll just call this one generic CK, or CN, oh, sorry. So N is how many there are altogether. K is just so we can keep track of which one. So in general, the height will be determined by the value of the function evaluated at each of the different endpoints depending on, each of the different midpoints depending on which interval we're in. So K just keeps track of which interval we're in. N is the number of intervals, okay? All right, so then the Riemann sum is basically just adding up all of the base times heights. So it'd be the sum from, so K, just keeping track of which interval, from 1 to n, since there's n intervals or n rectangles, and then we would just do base times height. But I'll write it in this order. So these are the different heights depending on which interval I'm in, times the base, again, depending on which interval I'm in. And so there is the notation for, in general, for a Riemann sum. The sum of all these different heights times all the bases, which again have the same distance because we like to split it up evenly. You add up all those base times heights, base times heights, base times heights, up to n of them, and you've got yourself an approximation for the area. So the next video will continue from here.